Hi, my name is Kimberly Leonar. I'm a Principal Big Data Engineer here at LSI, and I'm going to be discussing big data analytics and how to dramatically boost performance. Today we're going to talk a little bit about the facts about big data, and then we're going to go into characterization of the big data storage. What does the I/O pattern look like, and what do we know about it? Finally, we're going to talk about some of those real storage challenges that we see in the big data ecosystem, followed by storage performance features for some clusters. Following that, we're going to talk about some of the real-world solution and acceleration examples, including LSI storage solutions as well as HBase. Lastly, we'll talk about cluster management features, and then we'll go into a quick summary. So first of all, let's talk about big data and what is big data. So in the past 3 minutes alone, 183,423 hours of music have been downloaded, 141,000 apps were downloaded, 3.9 million videos were viewed on YouTube, with 60 million photos viewed, 300,000 new tweets, and 18 million Facebook views. So what does this mean? That means that we've transferred almost 2 petabytes of data in the last 3 minutes alone here on the planet Earth. In addition, almost 400,000 petabytes of data was stored. Let's discuss the smarter planet. Nowadays, everything is interconnected. And who's driving this data? Well, as an example, people to people, things like Twitter and Facebook, sending blogs, texting, and people to machine, logging into your computers, healthcare. They're measuring respirations, your heart monitor, click streams. And finally, machine to machine, and this is really what's driving the majority of the data that's being generated today. These are things like surveillance systems or even sensors on bridges. You'll often hear the 3 V's being discussed. The 3 V's are volume, the sheer amount of data that's coming in, the variety, the different kinds of data that are coming in from different sources, as well as velocity. More and more people are being connected, more and more machines are being connected, and we're driving more and more data. However, there is value in retaining some of this data. Finally, differentiation. By gaining a better insight to your business and your customers and your market, you can become more competitive. You can improve your efficiency. You can gain great insights about what makes people buy things. And you can also improve your profitability. So let's discuss a 24-hour data footprint. So this is me a couple of weeks ago. I was giving a presentation out in Las Vegas. When I landed, I made a phone call. Hi, Mom, I'm here. Then I went and I sent a tweet. I'm ready to rock this data deluge. Got into a cab, said, take me to MGM. Again, another credit card transaction being stored. I get into the MGM and there are cameras everywhere, video surveillance all over the place. Smile. Finally, checked in, got my card, went to my room. What a cool view. So I had to go get on Flickr, make sure I put this picture up. Then fell behind on some of my work, so I read 178 emails followed by 22 emails that were sent. Called the kids, said goodnight, went out to dinner. Again, another credit card transaction. Got back to the room, ready to rock again. I'm on Facebook, I'm YouTubing, I'm on Netflix. And then finally we show up at the presentation. My 24-hour data footprint alone, it's growing, just like everybody else's, but we're storing gigabytes of data absolutely every day and every person, and there's information to be found in this data that we're collecting. So let's characterize some big data storage. First of all, let's start out with some basics. What is Hadoop? Everybody's heard of Hadoop, and yes, it's an open source software framework. It supports data distributed applications. The whole point of Hadoop is to be able to scale out your architecture as opposed to scaling up your architecture. It's a shared nothing architecture, which means each one of these nodes that's in a cluster acts independently. It has its own processing power. It has its own data. The point is, you move that processing to the data. You don't move the data to the processing. There's so much data, it's too heavy to move to the processors. So this is exactly contrary to what we've been doing over the last couple of decades. Finally, it leverages inexpensive commodity hardware. And what that means is that it handles built-in failures. By default, each piece of data is copied 3 times throughout a cluster, so that if a server were to go down or if a disk were to go down, there are still 2 copies of that data available. So it's very highly available. And because of that, it doesn't necessarily rely on RAID. The Hadoop platform has three different parts. First of all is the HDFS file system. This is a user space file system that allows you to show all the data across multiple nodes from one place. So from the HDFS, it looks like you have one big huge file system, but under the covers, you have a little bit of file system on each one of those servers. It makes management a whole lot easier. Secondly, you have the MapReduce implementation. We're going to talk a little bit more later about what MapReduce is. And third, we have the Hadoop Common Framework. And what that is it allows you to take one big job, cut that into multiple small jobs, and send that off to each little individual server to do their part, their task. The next thing we're going to talk about is what is HBase. So HBase is also an open source scale-out NoSQL column-based key value store, and that's a lot of words. It just means that it's a database. It has database-like qualities, but it doesn't require that you have fully constructed data in advance. So remember that variety thing we talked about earlier? This is why this is so important, because there could be so many different kinds of data that are coming in so many different formats. You want to be able to store them all without knowing in advance necessarily how the data is going to be brought into you. HBase is deployed on approximately 30 to 40% of all Hadoop installations across the world right now, so it's very popular. It's designed for low latency random access to data that's stored on the Hadoop platform. Now, one of the things about the Hadoop platform and the HDFS file system is each chunk of data by default is 64 megs. That's a very, very large size. And the reason for that is because it's meant to be able to sequentially go through lots and lots of data. So HDFS is actually meant for large sequential accesses. However, HBase, as you can see here, is designed for low latency random accesses. So what that means is there's a little bit of data acrobats that we have to do to make this work on top of an HDFS file system. Finally, it's a scale-out table store, so you can actually do a lot of row-level updates over massive amounts of data. So as your database gets larger, it takes in it, the word here is shards, it takes in it shards that data across the servers, and you don't even have to worry about doing that. Now, one of the things about HBase is that data is written in there sequentially. So as you write to HBase, it's just written to what we call an H log, which is also known as a write-ahead log. So writes are very, very fast, because even with spinning media, you can write very quickly sequentially. So your inserts and your updates, they happen very fast. The challenge is reads. So in order to combat the fact that every time you want to try and do one read, you have to do a 64 meg or larger chunk read, what it does is it maintains an LRU cache in host memory so that reads can be serviced from memory. The problem here is that data sets that are larger than that host cache, wow, that's a challenge, because now we have to go down to spinning disks and ask them for a small piece of data. So HBase is a fantastic application as a NoSQL scale-out key store. However, there are a lot of data acrobats that cause a lot of challenges here. So let's talk about MapReduce. MapReduce is it's a very normal way of solving problems. If I asked everybody to take and count all the cups and all the glassware in their kitchen, you would all do it the exact same way. If there was 10 of you in that kitchen, you would assign maybe each one to a cupboard, or one would count plastic, one would count glass, one would count spoons, maybe one forks. But it's just a way that you would take and you would give each person a part of the problem, and that's really what MapReduce is. It's a data transformation based on key value pairs. When you map, you take and you break a set of data into key value pairs, which are also known as tuples. Now, reducing is just taking that output from the map and combining it into smaller sets of tuples. So you might have one answer, or you might have many answers, depending on what you've asked this MapReduce to do. Not a lot of the data that we do right now is really intrinsically key value in nature, or it can be represented that way. So you can see down here in the examples below, I had a class once and I asked them, we're going to use MapReduce to count the number of words on the first page of Moby Dick. And here you can see I did an example. The key would be call me Ishmael. So call, the value would be 1. I saw that word once. Ishmael, I saw that once, and so on and so on and so on. That is what mapping is. It's very simple. Now you would take the output of that and send it over to the reducer, where we would take and combine those. So we saw the word call twice. We saw the word Ishmael once, mouth twice. It's very, very simple, but it's very powerful. That's part of the power in it. Again, also on product social sentiment. Social sentiment is very important these days for companies. You need to know how your customers feel about your products. So again, you could see a key might be that was a great price, or wow, that was exactly what I needed, or yeah, that was just okay, or a waste of my time. So you would actually take and you would pull a value out of that one. And their value might be it was a positive response, or a negative response, or it was a very neutral response. And overall, you can ask a question, what do people think of this new product? You could take and put that into a MapReduce problem, and you can have a result very easy. So it's a very, very simple processing. So let's talk a little bit about the MapReduce data flows in Hadoop, because one of the things about Hadoop is that there are a lot of different parts of the problem. Now, I told you about mapping and I told you about reducing, but there are some intermediate parts. So first of all, when you ask a problem and you submit a job to Hadoop, the first thing it does is it acts on the files that you've asked it to do. So it's going to do very large sequential reads through those files that you've told it are important to you. During this time, we see a lot of high disk bandwidth. There's not really much network bandwidth. The only network bandwidth that's going on is making sure that each of these tasks are getting completed. So secondly, we do something called spilling. So as we're mapping, we take that little temporary answer. Yes, this was a great product, 1. No, that was a terrible product, 1. We might see those, and we will take and we'll store those first of all in host memory, but eventually you're going to run out of space on host memory. So these temporary answers are going to be spilled over in what we call spill files. Then those go over into disks. So when these spill files happen as it's going through and doing the mapping, it's writing these little teeny tiny files off to the disk. So keep that in mind as we go on and we talk about combining. So finally, when it's done doing all the mapping, it has to take all these little pieces of the answer that it spilled into these spill files and combine them. So now it needs to go through and count them out. Finally, it needs to sort and partition them. So during this time, we see very low to medium disk bandwidth and low network bandwidth, but there's a lot of random I/O going on in addition to sequential I/O, and that could be a real challenge when you're talking about rotating media. Finally, we're doing the shuffle phase, and the shuffle phase is when you take and you give the part of the answer to the reducer server. So this is the only part of the problem where we actually can't always bring the processing to the data. So there's a lot of data that's being transferred across the network to the server that's going to be doing the final reduce. Now there's usually more than one server that's doing the reduce. It could be every server in your cluster, could be 10,000 servers are doing a reducing, but more often than not, you'll have only maybe half or less of the servers doing reducing that were handling the mapping, and that's generally because your reduce output is usually much smaller than your map output. So during this time, we're seeing a lot of network bandwidth, but not a whole lot of disk bandwidth. Finally, the reducer is doing almost exactly the same thing that the mapper was doing, but it's doing it with those final answers, and again, we see more high disk bandwidth. So let's take a look. On the right-hand side at the top here, you can see a chart. Now, the blues are writes and the reds are reads. Across your x-axis on the bottom here is time. Across the y-axis is the actual disk LBA. So what that means is this is the part of the disk that we were requesting at a certain time. And as you go across to the right, you can see there's a lot of sequential I/O going on, but you can also see there are little tiny periods of writes that are random at a single point in time. So how do you summarize a MapReduce job? Well, sometimes there's a lot of storage bandwidth, sometimes there's a lot of network bandwidth. Sometimes, especially when it's trying to do some of the reducing, in fact, we'll go back here, during the spilling, the combining, and the sorting and partitioning, we'll see that there's a lot of CPU utilization going on trying to handle these files and manipulate these files. Finally, the spillover files will require some random I/O. And then there's a lot of spatial and temporal locality, as you can clearly see on the right-hand side, where there was a lot of the same LBA that's requested over and over again, or LBAs that are in close proximity to each other that are requested over and over again. And because of this, we realized that there are some opportunities that you can cache into very fast disks some of these temporary answers so that they can be recalled much more quickly as you manipulate that data. As an example, there is a benchmark called TerraSort. This TerraSort benchmark is not just for Hadoop. It's been around for many, many years. You can sort however much data you want, despite the name. But we did a 10 gig TerraSort. And all in all, during this TerraSort, it generated 58 gigabytes of reads and writes. So that's almost 6 times as much data that was actually sorted. So we had to read it, we had to write out temporary answers, then we had to read those temporary answers, and then we had to write them out again. So essentially each piece of data has been touched at least 4 times. So during this time, you have a lot of map and reduce side spills, the spill files, a lot of combining, a lot of partitioning, and they generate random I/O as they create and access and manipulate and then delete, finally, all those files. So let's talk about some of the real storage challenges in the big data ecosystem. Well, after talking to a lot of people that have deployed clusters, Hadoop nodes, thousands and thousands of them, I've decided to take and put together, and you can see it's a very long list, an abbreviated version of some of their challenges that they've come across. And this is very interesting because it's different than what you see maybe in somebody that's deploying, say, a database. So first of all, it's difficult to apply this one-size-fits-all mentality to a storage subsystem. As you saw in the previous slide, you know that rotating media is good at sequential. It's really slow at random, but it's even slower when you ask it to do both. And clearly, back here, you can see that sometimes we're asking it to do sequential and sometimes we're asking it to do random. It's a highly dense architecture. It's very DAS-friendly and SAN and NAS averse. And what that means is that your node real estate is very valuable. And sometimes just opening up that box and adding something is not possible. They're usually very, very dense. Third, data ingest and digest bandwidth. You want to bring data in very quickly from multiple sources. You also want to be able to read it quickly. So if you can bring in a lot of data, you can actually write a whole lot more data, a whole lot more files. You could bring in more sentiment analysis and things like that. So having as much bandwidth available to each one of these nodes in the server is very, very important. Finally, Hadoop is designed to deliver fast, and I'm going to put quotes around that because fast can mean different things to different people. But as you ask it to do something, if it takes you maybe 2 days to get an answer, you might ask a couple questions. If it takes 10 minutes to get an answer, you're going to keep diving in and asking more and more questions. So the faster your answers to your queries, the more valuable this data in this Hadoop cluster becomes for you. So finally, speeds are really critical if you're going to be doing something like real-time analytics or ETS type transformations. The fourth thing is Hadoop, unfortunately, treats all storage exactly the same. It doesn't matter if you've got faster storage or slower storage. It treats them all exactly the same. Currently, there are no data tiering or fast storage caching solutions that are available to put maybe more important, maybe hotter data on something that's more fast. Fifth thing is multi-software platform places super hard challenges on SLAs. So sometimes you have some competition for the data that's on there. You might have, for instance, a HBase sitting on top of HDFS. You have somebody that's doing some streaming HDFS reads, and on top of that, you're also trying to schedule some HBase random I/O. So there's a lot of challenges that are placed on this Hadoop cluster to do very different things. Finally, you want to make sure you keep costs low. More than anything, they're very, very aware and cost sensitive. So built on commodity hardware, and you want to make sure that the management is very simple so that they can have a lights out cluster. Some of the other ones, just real quick, is that we have a big data ecosystem which inherently causes an imbalance in those system resources over the course of the job. And you saw just a few slides earlier. Some of these things are things like HBase when it does checkpoints, when it does compaction, when it's trying to, HDFS will try and balance all the data across all the nodes. So that happens as well. Also, remember those HLog, write-ahead log writes? It makes those writes really fast, but at some point those writes have got to be committed down the disk. So when those happen, you have a big flurry of writes going down to the disk, and subsequently a lot of I/O going on that can be challenging to try to keep up with your SLAs. You have memstore persistent flushing, you got shuffling and sorting, data ingest and digest, and to use the word again, it's data acrobats. Also, managing that physical cluster is really a headache. So even trying to identify failed components, like where's my bad disk at? It's crazy. It's very difficult. So if you think about it, an MTTF of 4 years results in nearly 5 failures per week in a cluster of only 1,000 nodes. So you've got 5 failures a week that you've got to deal with. So making sure that you minimize your failures, or if there is a failure, that you can help identify where the failure is so it can be replaced very quickly is very important for management. So I was asked, well, what are these big data administrators doing now to address any kind of performance issues that they may have in their cluster? Well, your number one answer is just add more servers to the cluster. Hadoop's known for having a very linear scale out of performance. And if you take a look at this very small chart, this is just a 100 gigabyte terasort that I did. And across that x-axis, you can see there are 4 bars. One is 1 node, 2 nodes, 3 nodes, and 4 nodes. So as I added nodes, you can see a linear decrease in the time that it took to complete this 100 gig terasort. That's the fastest way to do it, and what most people prefer to do. Now, secondly, you tune your cluster or your job code. The problem is this is time consuming and very complicated. Not only do you need to know a lot about Hadoop and a lot about HBase, but you probably need to know a lot about your underlying OS, so be it Linux or Windows that you're using in this particular environment. So it's time consuming, but there's a big payoff. And let me give you an example. The big payoff that I saw, I was trying to tune a cluster just a couple of weeks ago. I was trying to push the bandwidth limits using a benchmark called DFSIO that comes with Hadoop. When I was initially running it, I was only getting about 2,200 to 2,300 megabytes per second, even though I clearly had a whole lot more bandwidth available to those disks. By just doing a couple, 5, 6, maybe 7 tweaks to my Hadoop cluster comp files, I got that number from 2,200 to 5,500 megabytes per second. So tuning is very important, and you can have a big payoff, and it costs you nothing. Third, you can add faster memory, faster processors, more disks, or maybe a faster network. There's a lot of things that you could do. And if you add more memory, for instance, you have a larger working set that's available in memory. That's very important for HBase, in fact. In fact, the way that an HBase administrator tells you nowadays, if I need faster HBase, I just go and I add more memory. Well, that's good up to a point, but part of the problem comes into adding more memory. You end up with garbage collection issues, and so you get decreasing return on investment as you add more memory. Secondly, you have to open up that server, or you got to plan in advance. Now, sometimes it's not bad to plan in advance, but people just don't want to go and open up 1,000 servers. That's usually just not an option. They would rather just go out and buy another server and add it to it. Finally, adding faster processors and maybe faster network, it really breaks that scale out versus scale up model that Hadoop is based on. The fourth method, and we're going to talk a lot about this in this presentation, is using flash. Now, your solutions vary here, but the good thing is that Hadoop is very well aware that there is flash available, and there's a lot of flash enabling features that are on the horizon. I'm going to show you some of them, but we have things like HBase bucket cache and heterogeneous storage, which is HFS 2832. Okay, so what are our storage performance features for their clusters? Well, we have the industry's broadest portfolio here at LSI for storage. We have the whole product line. We got your SAS HBAs, your RAID HBAs. We even have RAID that has integrated flash in an HBA or RAID controller. And we also have PCIe flash. So anything that you might need to build these intelligent clusters, we already have. Secondly, we have 12 gig SAS that we just welcome. So we've got up to 9,600 megabytes per second of bandwidth in one single controller. So in our Gen 3 SAS RAID, we can actually get up to over 720,000 IOPS, 6,000 megabytes per second on reads, and you can put together 240 disks. Great features. Now, on our Gen 3 SAS HBAs, over 1.1 million IOPS it can handle, and over 5,600 megabytes per second read with up to 1,000 devices. So this is really the key of what you're going to be building your clusters on. Well, let's look at Nitro Warp Drive as a big data solution. Nitro Warp Drive is a PCIe flash-based controller, and it comes up to 3.2 terabytes of enterprise-level eMLC flash. And it is a very dense form factor, and it's also fast in performance for both sequential and random access. Doesn't matter, you can ask it to do both at the same time, and it's just as fast. Very low latency. And also, it's great a target for flash acceleration software and features. And I'm going to show you exactly how we used it for that kind of use case here in a couple of slides. Right now, almost all Hadoop and big data database vendors have this particular Nitro Warp Drive in their development labs right now. They're doing test and validation for some of the new flash-based features. So you can bring your data even closer to the processing by using something like Nitro Warp Drive in your clusters. Now, next we'll talk about Nitro MegaRAID. Nitro MegaRAID is built on the MegaRAID RAID controller that's been available for well over 10 years now. And in addition, we actually added 2 flash modules on top of that. Now, the interesting thing about these 2 flash modules, they come in quantities of 100 gigs up to 800 gigs onboard flash, and you can use it for 3 different purposes. 1, you can boot off of it. 2, you can do what we call transparent caching, And 3, you can just use it to put your data on. Now the application acceleration feature that we have, it's transparent. All you have to do is turn it on and it automatically will identify hot data and and we also have read and write cache that is available in write through or write back mode. It's automatic, starts itself up, and it tunes itself up. So as your hot data moves, so does the hot data that we're keeping inside of this controller. And it kind of helps future-proof your Hadoop cluster. So as some of these features are available, you've already got the flash available to you. It also has very minimal CPU and memory overhead, and that's very, very important in Hadoop clusters. Some of the work that we ask these Hadoop clusters to do become very CPU limited. So you want to make sure that you're not taking any more of those cycles than absolutely necessary. Let's talk about some of the acceleration examples that we've done. So first of all, we're going to talk about Hadoop. So specifically HDFS and MapReduce problems, and how are we accelerating those? Well, the first one I'm going to show you is a new feature that we have for 12 gig SAS, and it's called Data Bolt. And what this does is this allows you to actually use your current 6 gig disks and combine them into a total of a 12 gig technology. So doing this, it allows you to have faster data ingest and digest speed. Data ingest being how quickly you can bring files into HDFS, and data digest being how quickly you could read those files once they're already in HDFS. Now you can see here, the green line at the bottom is where we have the data bolt turned off, and the performance actually was limited to around 4,000 to 4,100 megabytes per second. Impressive, but by adding data bolt and doing nothing but enabling a data bolt feature, we were able to combine that performance to take advantage of the Gen 3 PCIe Express, and we were able to get over 5,500 megabytes per second. So the files, not only were they written faster, but we were able to take advantage of the disk that we had combined in there. Next, we used Nitro transparent caching to reduce our TerraSort jobs. You might recall I talked about TerraSort earlier, this TerraSort benchmark. It takes data of the size that you request and it would just sort it. So how quickly it could do that is based on what kind of storage that you have in your performance characteristics of the storage. So what we did here was we did 2 different TerraSorts. The one on the left we did 50 gigs, and the one on the right we did 25 gigs. And we took those temporary files. Remember those spill files I talked about earlier? Well, there's a directory just for those spill files that you define, and it's called the MapReduce local directories. We just simply took and we turned on that transparent caching to those MapReduce local directories. That data very quickly became hot, and on subsequent requests we were able to read it from flash as opposed to going down to the hard disk and accelerate the entire process. So we got about a 30% reduction in the amount of time that it took to complete these jobs just by using transparent caching. The next one, we did exactly the same thing. We applied the transparent caching to the MapReduce local directories, but this time we ran a different benchmark. This one's called PigMix. And what PigMix does is it creates batch jobs. So you tell it what you want it to do, and it breaks it down into smaller pieces. So it will take the output from the first MapReduce job, and it will use that as input to the next one, and so on and so on. So you can see across here we have from L1 all the way to L17. This is the amount of time that it took with the caching applied as compared to the baseline where we had no caching. On average, this job completed about 25% faster just by applying transparent caching. Next, let's talk about TerraSort jobs using Nitro MegaRAID Flash, not with cache or transparent caching, but putting those MapReduce local directories directly on the flash. So by doing that, in this case here, you can see I was using an 8120, and that has 800 gigs of flash. So I put the MapReduce local directories directly onto that flash, and I did a whole terabyte TerraSort. And my baseline, it took about 400 minutes to complete this job. With it enabled, it took about 170 minutes. So we got more than a 50% reduction in the amount of time that it took to complete this particular sort job, and that is very significant. Now let's look at some of the HBase acceleration. So the first thing we're going to look at is the benchmark we're using is called YCSB. It's a very standard benchmark. It's called Yahoo Cloud Serving Benchmark. Now what we did here was we just took and we applied transparent caching not only to the MapReduce local, but to the HDFS files as well. So everything was being transparently cached. Without the cache, we were able to achieve about 600 operations per second. Once we enabled that Nitro Mega RAID cache, we got just under 1,800. That's a 3x improvement in the number of operations per second just by identifying the hot data and caching that. So it was able to help out that LRU cache that I discussed earlier. But there's other features that HBase has as well. These are the response time histograms with HBase. So each operation, as it completes, the response time, both the 99th percentile, 95th percentile, and the average response time are bucketized. Now here, I'm taking the average response time of YCSB benchmark, and you can see the green here. We have a really beautiful average latency that's centered around 1.7 millisecond response times. Now, without the caching enabled, you could see that, yeah, there's a lot of them here, but they tail out very, very, very far. And in fact, if I were to take and extend this x-axis, it would go to over 1,200. So the response time was very significant. Sometimes, yeah, they were very short, 1 millisecond or 2 millisecond, but many, many, many times they were several seconds, up to even several minutes long response times. So the new feature that HBase came out with is something called bucket cache. It's HBase 7404, and what we did here was we took advantage of this bucket cache. Now what this bucket cache is it is a tertiary cache, and it's what they like to call an eviction cache. So anything that doesn't fit into that LRU HBase cache will first get flushed into this eviction cache, HBase bucket cache, before it goes down to the hard drives. So what that does is it complements your host memory cache that you have. Now you can see along the x-axis, this is the time in minutes as we were running the benchmark and as it was getting warmed up. And we ran it for 90 minutes. And we took over 10-minute intervals the number of operations per second that we were able to achieve. So when they first started out, as the bucket cache is in the LRU cache and not warmed up, they're roughly about the same. But after about 40 minutes, you could see that they start splitting apart. And that Nitro Mega RAID bucket cache feature is really starting to show the benefits here. And it very quickly, between 60 and 80 minutes, climbs up from a minimum of 1,600 all the way up to about 13,000 operations per second. So a huge improvement in performance. Next here, we're going to show you what the same feature, HBase bucket cache, but instead of using Nitro Mega RAID, we're using Nitro Warp Drive. Now in this chart here, on the x-axis, this is the operations per second, and you'll notice that this is a logarithmic axis. So I'll show you what these numbers are here soon, but over here in the green, these are your with Warp Drive bucket cache feature enabled. So your operations per second are all the way out here, and your response times, both your average response time, your 95th and your 99th percentile response times, stay between 0 and 20 milliseconds. Now on the left side of the chart, you're going to see there's a yellow, and that's your average response time using hard disk with no bucket cache feature. And then you've got your 95th percentile, and then the red shows your 99th percentile as time in milliseconds response times. So huge difference in the response time and the operations per second. And this next slide summarizes what we found there. With the HBase bucket cache feature enabled, we were able to get just under 42,000 operations per second, and without, just over 1,000. So it's roughly a 40x improvement in operations per second with similar reductions in average response time. So I showed you a lot of HBase acceleration features, so I wanted to take and put them all together for you. The first one, the last one we just saw, is using Nitro Warp Drive as bucket cache accelerator. We got about a 40x improvement in performance. The second one I showed you was Nitro Mega RAID bucket cache, and we got about a 703% or a 7x improvement in the operations per second. Third one I showed you was using Nitro Mega RAID just as transparent caching on HDFS, and we still were able to see almost a 200% improvement in performance. Let's talk about some of the cluster management features that we have. Well, one of the important things is being able to manage your storage from one pane of glass. You don't want to have to go log into each one of those separately. So we have a great CLI tool set and a fantastic web GUI that allows you to do that. That's a really outstanding enterprise-level feature that LSI can provide to these administrators. Finally, if they're using the RAID controller, they can still do automatic JBOD configuration for fast Hadoop deployments. Now, as I mentioned earlier, Hadoop is not based on RAID. It inherently has failures built into it. So in general, what you want to do is you want to set up each disk as a single disk RAID 0 in this kind of configuration. So being able to automatically do that with one mega CLI command is very important. Finally, disk identification, very, very important. Just being able to send a blinking light so that they can find that failed disk and pull that out. That's very important. Finally, the feature-rich RAID to protect your most valuable nodes. In a Hadoop cluster, there are some nodes that are, let's face it, more important than the others. The two that are really important for Hadoop are the name node. The name node is the node that keeps track of where all the data is located throughout your cluster. It's a single point of failure, and if that name node goes down, so does your cluster. Currently, there is no name node HA available. The next generation of Hadoop 2.0, which is on the horizon, does have that available, but it's not automatic failover. So making sure that you can keep those servers up is very, 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 very important. Now, secondly is the job tracker. The job tracker is the manager of the cluster. He's the one you submit your jobs to. He breaks up the jobs and appropriates it out to each one of the nodes in the cluster that can do work. Again, another single point of failure. And also for HBase, we have what's called the HMaster. And the HMaster does similar to what a name node does for HBase. So keeping those three nodes up is very, very critical. Reduced mean time to data loss. We have features like patrol read and check consistency that does media scanning and repairing so that we can find out if there's any kind of failed LBAs that are available before we try and read it and have a failure on that. Also, we have a feature RAID 0 copyback. The last thing is boot volume support, and this is a feature found in Nitro Mega RAID that allows you to actually use those two onboard disks as boot. So that way, if you've got valuable in-the-box real estate, you can take those big spinning disks and you can use those for HDFS data, which you're very good at, and you can just use the onboard for booting. Or you can use it for boot and flash-based cache, which a lot of customers like to do. So in summary, there are a lot of applications that sit in these Hadoop clusters that create crazy storage challenges. But the good thing is there's a lot of flash-aware features that are allowing an economical, and that's a very important word here, acceleration for big data infrastructures. We have the HBase bucket cache feature, which we showed you shows up to a 40x improvement in performance. And also, by building your clusters with something like Nitro Mega RAID or Nitro Warp Drive, it allows you to future-proof now because there are a lot of different features on the horizon that will enable you to use Flash in a cluster to accelerate the important data. Nitro Mega RAID's transparent caching also allows you to enable acceleration on applications that don't have a custom cache or acceleration capability like HBase bucket cache. So we've used it to accelerate things like MongoDB and Couchbase and even Hive. 12 gig SAS enabled Databolt gave us up to a 30% higher data ingest and digest speed using your current 6 gig disk technology. And also we have enterprise storage management features for simple cluster management. Here are some of the resources that I used for this presentation. Thank you for attending.